Hey everybody, welcome to EEs Talk Tech. My name is Mike Hoffman.
And I'm Daniel Bogdanoff, and today we have Matthew Warner, who is a metrologist for Keysight Technologies. So you're here to tell us about the weather or something?
That's right. At least that's what my doctor's office thinks I do.
Okay. So why don't you tell us a little bit about metrology as a whole?
Yeah, so metrology is just the study of measurements. So anytime someone wants to make really accurate measurements, they're typically a metrologist or have studied metrology, though some of them like to still say they're engineers.
Okay. And today we are talking about the basic ways that we actually measure the universe. And we call them SI units. And you want to give us a brief overview about SI units as a whole?
Yeah, I'd love to. So SI units are essentially the basic units that are used, and all other units are derived from that. So there are 7 of them. I had to give a cheat sheet because I only really work with 2 or 3 of them. But they are length, mass, time, electrical current, thermodynamic temperature, amount of substance, and luminosity.
Okay. So why do we even have SI units as a thing?
Yeah, so it really comes down to commerce. So let's say, what do you want to buy today? Milk. Let's say you're going to go buy milk. So at the store, we have standard units of gallons or liters if you're in a country that uses SI units normally. But before we had a common system of units, it'd just be like, well, here's a handful, or here's this mug. And if this mug's not the same as another mug, it's really hard to do business that way.
That makes sense. And I know that trying to rig scales and negotiating over the method of measurement has kind of historically been a pretty big issue for commerce as a whole. So it's like, okay, I need a yard of cloth. What's a yard, right? So I think you told me this, the way they used to measure a yard.
Yeah, they used to measure a yard from the tip of your nose all the way to the tip of your finger, and that was a yard.
Okay, so yeah, it's great.
Seems very reliable.
Yeah, so in that case, since I'm taller than both of you, I'd be the yard cloth buyer.
Right. And not the cloth seller.
And not the seller, yeah, that's right. Yeah, and actually, interestingly enough, the term ruler comes from, this is a problem that went back all the way to Egyptian days. And so the term ruler actually comes from the idea that, well, we're going to measure the yard based on the king's tip of his nose to the tip of his finger.
Oh, that's pretty cool.
Yeah.
Bonus fact, I like that.
That's right.
Huh. So ruler as a term for measurement came from ruler as like a monarch.
That's right. That's right.
Interesting. I didn't know that. So it's definitely very important to make sure we're all talking about the same thing. So, there's the famous lost space vessel. I don't remember the details of it, but someone was using metric and someone was using imperial standards, and all the measurements got messed up, and they lost a satellite or something. So it's important to be talking about the same thing. How do we actually know what makes, there are 6 of them. What makes a yard, or a meter, I guess?
There's 7 of them. So back in the day, they sort of were all defined on physical characteristics, but now they're all defined by sort of certain physical constants that we find in the universe, with the exception of the kilogram. And I think we'll talk about the kilogram a little bit later.
Yeah, that's a cool one.
So the kilogram is actually a physical artifact, and they all started as physical artifacts.
So like something tangible, so like a yard or a meter was a meter stick somewhere that was the meter.
That's right, yeah. And then over time, there are various problems with that. But mostly, a lot of it comes down to someone like the United States doesn't want to be dependent on France to hold the kilogram and to have all this power in sort of commerce. The other thing that happens over time, and we see it even with sort of the kilogram, is that the value of the kilogram will change over time. So, and different, if we track, so there's the kilogram, but then the United States also has a kilogram. And if we track the kilogram versus a kilogram, they actually change against each other over time.
How?
Yeah, isn't the kilogram the artifact itself is an object that can lose mass over time or what have you? A kilogram
yeah.
isn't it like some certain number of a certain atom or something like that?
So that's a good question. So right now the kilogram's being redefined. So it's not officially been redefined yet, but it's currently in the process of being redefined. And there are two thoughts on this. So one is people are trying to define the kilogram as, it'd be sort of like a certain number of carbon-12 atoms.
A
mole
quantity,
or
which is
something.
another SI unit.
Yeah, a quantity of
A mole. Yeah.
a quantity of a certain type of atom. But the other way that they're trying to do is they're actually trying to relate it to Planck's constant using a watt balance.
And watt balance is really cool. I don't want to get there quite yet. So you said, the kilogram gains or loses mass over time. How do you know? It is literally the standard of mass
Yeah,
that
right.
we have.
It has zero measurement uncertainty. So technically, by definition, it doesn't. But everything else relative to it does. Now, we can look at, if we're looking at mass.
It's ridiculous, right? It's a totally ridiculous concept.
It's a little
Yeah, it is.
catch-22 there.
It is, yeah. But if we look at mass, there's a lot of different ways that a mass can gain or lose weight. So if you have a mass and you drop it, it might chip and it might lose weight. Alternatively, if you take a mass and put your fingers on it, your fingertips have weight, and you've now
Oil.
just added to, your fingerprints have weight, so you've now added to.
Or if it's
Mass.
exposed to air and it oxidizes non-noticeably.
Or even if it's in a vacuum, wouldn't radioactivity of that particular thing eventually shed mass in some way, shape, or form?
Maybe, I don't know.
Yeah. Come on, you're supposed to know this stuff.
What is the kilogram made of? I don't know. Is it some sort of?
I think it's platinum, but I don't know
Platinum
for
or
sure.
something?
It's like
Okay.
a perfect
Research it.
it's a perfect sphere. It's like the roundest object in the world.
It's pretty
actually,
beautiful, yeah.
There's some really cool YouTube videos you can find on what this object is, and I want to say it's some sort of something that has a very very long half life, so it doesn't have that radioactivity issue necessarily. It's like carbon-23 or something or 14, but yeah.
And then they have like sister units that are replicas of the kilogram that every once in a while come back to be checked by the kilogram.
That's right, yeah.
Yeah, and they call them conferences, something like that. And there's a whole thing behind them. It's interesting. And over time, you would expect and you would hope that the home kilogram stays right smack dab in the middle of all of them, and all the other ones are kind of changing up and down on average in a flat line, but that's not necessarily the case.
So that one's the big question mark, but it sounds like the other ones are you said defined by phenomena or constants in the universe.
That's right.
So give us an example of that.
Okay, so if we were to look at the second, it's defined by, it's a little bit less than 10 billion vibrations of a cesium atom.
Interesting.
Yeah, and so length is defined, so the meter is defined as the amount of time light will travel in a vacuum for essentially 1 over c. So 3 times 10 to the 8th.
Huh.
And sorry, if we're hearing space noises in our headphones, so if you're hearing space noises out there, I apologize.
It's a real spacey subject. It's kind of fitting actually. I feel like I'm like some sort of episode of the universe or
I
what
know,
have
it's
you.
kind of like the old radio sci-fi sounds. What was the question? I forgot the question. I had a good answer, though.
We were talking about the second and how there's
the
certain
CCNet. Yeah, so my question was, does that change with respect to, we know it changes with respect to gravitational acceleration. Is there a standard on which that has to be measured? So sea level?
So what I've read is that it changes the most based on magnetic field.
Oh,
So if
interesting.
you're building a cesium standard, so a cesium reference standard, what you'll do is you'll apply a magnetic field to it that's known, and that is much larger than the Earth's magnetic field.
Okay, so counteracting all the earth noise.
And then you get rid of that error.
Interesting, that makes sense. I imagine there's some shielding and a lot. Is it a pretty expensive standard?
Oh, it's
Build.
not too bad. But the biggest problem that you have with the cesium standard on its own is it's really, really accurate for a short period of time, but it doesn't tie into any of our clocks. So the other thing that they had to do to tie in the cesium atom into your clocks is you'll actually use GPS. So GPS, in order to position accurately, will they have really accurate cesium or rubidium standards in all those satellites, and then you will have to sync your cesium standard with those satellites to get sort of absolute time rather than relevant time.
Yeah, because the accuracy, like checking the time on your phone, isn't nearly as important as checking the accuracy of a GPS locator on like a missile or something, right? So we could check in and be off by a fraction of a second every so often, and it's not a big deal, right?
Yeah.
Yeah, and generally, like the error that we're talking about for a cesium standard is like 10 to the minus 10th. It's tiny.
Right. Are there any standards that are, so far the ones we've explained are kind of intricate and have a lot of variables? Are there any that are simple without these kind of complications of worrying about magnetic field and things like that?
The killer.
I feel like that one's the most difficult one so far.
It's the most simple of all standards because whatever that weighs is 1 kilogram.
No.
For now.
Yeah, so
fair enough.
So what you're sort of touching on is how many primary standards are there? So a primary standard would be something that directly measures these physical phenomena. And by the way, there's not actually a primary standard for
I was going to say, so far, even the ones you've explained are referencing other measurement standards. Like you said, to measure a meter, it requires time.
That's right.
So is it...
Well, so time's the most accurate standard we have.
Okay.
Why? It just is the lowest error.
Yeah, it just has the least uncertainty. I don't know why.
So what is a meter then? Let's walk through them a little bit.
Okay, so the meter is defined as the speed of light, speed of light in vacuum over a certain period of time, which is right.
Which is something we know.
299 times 10 to the 8th.
And it's not, so there's like base SI units and derived SI units.
That's right. Yeah, so something like area would be a derived SI unit.
Right, because it's length times length.
That's right.
Right, or velocity is meters per second.
Yep, that's right.
Okay.
And even something like an angle, which has no units, is actually meters over meters.
Right. Based on SOHCAHTOA.
That makes sense, yeah. Meters over meters, no units. How do you... I don't want to see the proof of that, actually.
Pythagoras theorem, isn't it? To an extent.
Yeah, and angles,
Oh,
I guess so, yeah.
If you make a triangle out of it, you can divide it by the...
In that case, I don't need to see that proof.
Yeah, that's we're bringing it back to 8th grade.
Yeah,
we'll skip that.
It's been a little while. Okay, so meters are the length of time light travels in a specified amount of time.
That's right.
And how specific is... I mean, obviously, it's very specific.
Very specific.
Is it like a random amount of time?
No, it's
2.99 times 10 to the 8th.
Yeah, we have even more significant digits here.
Okay. What else do we have? So
299.792.4858.
Okay. Time. So it's based on the speed of light. I guess that makes sense.
So we've gone through time, length, weight. Let's talk about electric current. Let's bring a little double E action into it.
Okay, electrical current. So, and once you see how this is defined, you'll realize why there's no primary standard for it. But the electrical current is a constant current which if maintained through two straight parallel conductors of infinite length and negligible cross-section, placed 1 meter apart in a vacuum. That would produce equal force to 2 times 10 to the minus 7 newtons.
Jeez, I thought it would be like counting electrons or something. That's
yeah.
And that's 1 amp.
And that's 1 ampere.
So we just need to find some infinitely long, infinitely parallel
vacuums,
negligible cross-section conductors in a vacuum. And
yeah, that's right.
So
and then done.
Working on it.
But really, it's a flow of electrons. Do you know why they ended up with that method? It's obviously mathematically derived.
Yeah. So let's see. I'm sure it's based on mu naught of the magnetic field. I'm trying to remember what theory that was from electromagnetics way back in the day.
Okay. Yeah, I don't remember off the top of my head either. Maybe one of you who is listening can clue us into that one, because I don't know either.
Yeah. If not, I'll have to Google it.
Yeah, we'll definitely Google it afterwards. Yeah, got to be mathematically derived. So how do we measure it?
Yeah, so actually, we are able to have primary standards for voltage and resistance. And then, so since this is a double E blog, V equals IR, and you can get current that way.
Okay, so we have a very good idea of what voltage is set, but that voltage is actually a derived standard from amps.
That's right, yeah. So there's actually a number of primary standards that we have for derived standards. So wavelength of light has its own primary standard.
Okay.
And essentially what that is they have some material that is a really, really good notch filter. So you can sort of span a laser across that. And then when you don't see anything, you're like, well, now I know I'm at exactly this frequency.
Okay, that makes sense. Interesting. So we can measure voltage really well using a Josephson junction.
That's right.
I think. And then, which is a whole nother conversation. And then how do we do resistance? How do we know?
Well, NIST does it. No,
NIST.
but they have let's see,
National
maybe I
Institute
wrote
of Standards and Technologies?
That's right.
Okay. And they're based in Boulder, Colorado.
Gaithersburg, Maryland,
Oh, it's
and Boulder,
kinda like Boulder. Okay.
Colorado.
Yeah, I've been to the one in Boulder. It's pretty cool. They got a ton of our equipment in there, actually.
Yeah. Do they have a tour or something? I want to go see.
I was there to do some training, and
Okay.
I got a little mini tour out of it
Nice.
as well. It was pretty cool.
Very cool. So I don't know if you answered the question. How do we measure resistance?
I don't know
Well,
for sure. So
okay.
they have something based on some of the quantum principles of
Okay.
electrons moving.
Okay. Interesting. We need a physicist out here for that one.
So it's not somehow derived off amps. It's like if you put so many amps with a certain amount of voltage across a material.
No,
to
the
measure its
primary
resistance.
standard is resistance.
Okay.
So we have one for voltage and one for resistance.
Okay. So those aren't derived from amperes being the base.
Yes, because we have no way to, in actuality, make a vacuum that's infinitely long. So we don't. We're able to measure more accurately through some of the quantum effects and quantum tunneling and superconductors.
Yeah. So maybe let's talk a little bit about the volt then. Well, no, I don't want to talk about the volt yet. What other standards do we have?
So the next one's going to be temperature.
Temperature. Okay.
Okay.
So good old Lord Kelvin.
Yeah, that's right. And so it's defined based on the triple point of water.
The
Triple point?
triple point. Okay.
Yes.
Really?
Yeah, so the triple point of a substance, not all substances have them, is where you have gas, liquid, and solid coexisting in equilibrium. And that's at essentially 0 degrees Celsius or 273 degrees Kelvin.
Yeah, because I know the Kelvin scale is zero based, zero being no motion whatsoever. But then the scale of it, so is that where it's derived from? 273 is the triple point, and that's how they created the scale for Kelvin?
Yeah, that's right.
Why'd they pick 273?
Because they came up with centigrade first
Mm.
for the 0 and 100, and then they liked that, and it was a lot of work to change that, and all the previous scientific work that's been done.
I just realized where the word centigrade came from. Is it's a grade between boiling and freezing in 100 parts.
Yeah.
So
That's right, yeah.
if you didn't put that together before now, you're welcome. There you go.
Now, I remember one time learning about the history of the Fahrenheit scale, and it's kind of I don't know if you know anything about it. Dude,
I don't.
it's an interesting story. I believe it's a gentleman who was trying to create his own standard because back in the 16, 17, and maybe even the 1800s, being a metrologist was big money, right? People would come to you and say, measure this for me because I don't have the tools. And so people were developing tools to measure stuff, and he was trying to essentially monetize it by creating his own scale. And I think he named it after himself. There's an interesting story behind it. Maybe the listeners would be inclined to go do their own research, but it's kind
Yeah,
of
or
a
maybe
funny
we'll
story.
let you do lead a podcast on that one. That sounds pretty cool.
Challenge accepted. All right.
So if you want to see that, let us know. Yeah. Interesting. So temperature, okay.
Temperature.
So Kelvin, and we work off of Celsius for science things. So
Yeah.
that one's pretty easy. How a triple point of water at 0 degrees Celsius?
Yeah. So the triple point sort of has a predefined pressure. So we change the pressure. So
Okay.
here we are in Colorado. Water doesn't boil at 100 degrees C. It boils at like 96.
Yeah, try making rice here, right?
Yeah, that's right. You have to cook it an extra 15 minutes.
Yeah. That was an unwelcome shock. the first time. Like, man, this is crunchy. Yeah. Okay. Okay, so it's set pressure. Is pressure's not on there, is it?
No.
So that must be a drive standard off of
Yeah.
what? I don't know.
So there's definitely a length involved.
Yeah.
It's probably force over in length area.
Okay. And force is also derived. Right?
That's right. Yeah.
Like
okay.
PSI.
Yeah, interesting. Okay, what else do we have?
So the next one would be moles and amount of substance.
Okay, amount of a substance. I'm going to go walk around so the lights turn back on. Keep going. So the amount of a substance.
Yeah. So and that's just basically defined based on carbon-12 atoms, and so there's a specific weight, and I think it's here. I've got it. 0.12 kilograms of carbon-12 will give you a mole of carbon-12.
Wait, so the mole actually changes with the kilogram? Is what I'm hearing? So a mole.
That's right. That's right.
So actually, getting to the watt balance is going to be pretty monumental for molar mass as well, or quantities.
I mean, mass is involved in so much of what we do. Now, of course, if you're at home and you have a bathroom scale, you're not going to notice a difference.
Right, so I have 10 fingers, so after we get the watt balance, will it change?
Do this, lose a couple cells. Oh, just lost some weight. Nice.
That's right. Well, actually, NIST has a homemade watt balance that you can build, and you can get 1% accuracy or something like that out
That's
of it.
pretty good. Okay, we keep hinting at the watt balance. What other SI units do we have?
So last one's luminous intensity.
Luminous, so candela,
Yeah.
something?
Candela.
Candela. Oh, there we go.
Yeah, and that's just defined by it's going to use other SI units, but it's
Okay.
it is a source that emits monochromatic radiation of a certain frequency, and that has a intensity of 1/683 watts.
Okay, so it's a
For a certain
wattage
angle,
based.
yeah.
Okay.
Watt and light, because it's for a certain angle, or watt and length.
Is there phase involved in that at all, or is it kind of doesn't matter so much for intensity, I guess?
No,
It's
I don't think it matters because, actually, if
it's a
you think about
vector, not
most light sources, they're all random phase randomizers anyways. So it's all, the lights that we have going on here they all have random phase for the most part.
Yeah, makes sense. Awesome. Okay, so the watt balance. So we're getting away from the kilogram standard at the traditional kilogram standard. How long has that been around? Do you know?
Since the French Revolution.
Okay, back when people wanted to eat the same amount of bread.
That's
not
right.
die.
Yep.
Okay, goes back to having food every day, like we were talking about earlier. Okay, so tell us a little bit about the watt balance, because it's actually it is a feat of electrical engineering in my mind.
Yeah, so the watt balance is kind of interesting. So, by the way, this new one is the fourth watt balance that they've invented, or that NIST has invented. So NIST is now their fourth iteration of watt balance. And actually what they've been doing in the past is they've been using the watt balance to measure Planck's constant.
Okay.
And then someone had the idea and said, well, we know Planck's constant to, 1 part per billion or something like that.
Can you give us a brief refresher on what Planck's constant is? I remember using it in physics, but I'm not sure I could.
Yeah.
This is a complicated one. Strap in.
Sorry. So I'm not a theoretical physicist, so I may not be the best at this. But essentially, the idea behind Planck's constant is that all energy is discrete.
Sure. Okay.
So it's not continuous. And so Planck's constant is the smallest amount of energy that exists in a photon of light.
Okay. Great. Anything below that is just chaos, or it doesn't exist.
The current theory is it doesn't exist. Okay. So there's like a smallest amount of energy that light,
it's like the fundamental unit of energy.
Yeah.
This Planck guy really loved his units. There's a Planck length, I believe, and a Planck time as well.
Yeah, and it's funny, he actually came upon it by accident. So Planck, the study of it was all about blackbody radiation. So I don't know if you guys took astronomy, blackbody radiation, but essentially the thought is something of any amount of temperature releases energy. So for us, it is infrared energy, but for like the sun, it's visible light, and it's yellow because emits the most yellow and green photons. And so they were trying to figure out, well, how does that work? And Maxwell Planck, I don't remember his
Sounds
full
right.
first name.
Yeah, yeah.
It's definitely Max. Introduced this idea of Planck constant to make the math easier for him, and he figured it would cancel out.
Oh, that's awesome.
And then he got to the end, and he's like, well, it didn't cancel out, but the math now works. And then we've ended up finding tons of information about this. So without going into all the details, because I really can't explain it, but the idea behind the Watt balance and using Planck's constant as a sort of physical phenomena for mass is, so you're all familiar with Newton's equation, energy equals mass times the speed of light squared.
Yep.
But then Planck's equation is that energy equals...
Did you say Newton's equation?
Sorry, Einstein.
Yeah.
I did say
I was
Newton.
like, wait a second.
But Planck's equation is that energy equals Planck's constant times the frequency.
Okay.
And so you can do a simple substitution, say, we know mass is related to Planck's constant.
Interesting.
But so then how we do it for a Watt balance is actually pretty interesting. So it ends up using Planck's constant in a couple different ways. But essentially, if you have a mass or a balance, you have two sides, and essentially each side you'll put a weight on it.
Okay.
And
this
then
is
you
the Watt balance again.
This is just a regular balance.
Oh, straight. Yeah. Okay. Sorry.
And then gravity will apply a force, and then you can compare the masses.
Sure. And the force is applied.
When it balances, then the force is equal and the masses are equal.
Okay.
So the idea behind the Watt balance is, what if you were to replace one of those weights with electromagnetic force?
Okay.
And then what you can do is you can apply electromagnetic force to balance out mass. And then you can define, you can define mass based on Planck's constant and the current applied.
Okay. So, talk about that a little more. So, what does this look like in practicality?
Well, it looks giant in a vacuum in a
So
big laboratory.
Okay, it's in a vacuum. So,
Yeah.
must be. I'm not familiar with standard vacuum chambers, but I imagine this is bigger than your normal vacuum chamber.
Well, it's got to be huge because the Watt balance is probably, it's at least the size of this table.
Okay, pretty good size.
So the one that's really accurate is at least.
So you, instead of a weight on one side,
Mm-hmm.
you apply a voltage, or
You apply current, because what you really have is you have two permanent magnets, and then in between that you have an electromagnet.
Okay.
And so the first thing that you have to figure out is, what is the magnetic field? And the way that you do that, now we're going to bring in other SI units like length.
Yeah.
But the way you do this, at length and time actually, the way you do that is, if you take the electromagnet, you don't apply a current to it, and then you move it at a constant velocity, you'll get a voltage. And that voltage will allow you to figure out what your magnetic field is. So that's sort of like the calibrating of the Watt balance. And then what you'll do is you'll apply a current through the electromagnet, and you put a mass there, and what will happen is the electromagnet will apply a force upwards.
On the
mass,
permanent magnet.
On the permanent
Upper
magnet.
arm.
Mm-hmm.
Right.
The magnet will apply a force downwards, and then you can balance it out.
Okay.
This seems very elaborate. And it seems like there's a lot of variables here, right? Is the strength or efficiency of that magnet constant over time? Do you have some sort of calibration routine to see if it's,
Well, right now you can compare it against the NIST national standard.
The kilogram?
Yeah, the kilogram.
But I thought the kilogram was the easiest one. You're saying that was the simplest one.
You said, what is the most simple of them? It is the most simple, and it's probably the most easiest, but it's definitely not the best.
It's a huge problem trying to figure out how you have this thing in a mass in a vacuum, but the scale on your bathroom floor isn't in a vacuum. We're not all walking around in vacuums. So at some point you had to transfer the mass from in a vacuum to out of vacuum, and that's actually a really hard process.
Oh, because once you determine the mass precisely, then to do anything with it, you're exposing it to air probably, and so we're going to still see some sort of physical airtight type kilogram standard. It's just going to be checked against a watt balance that we know to be more consistent than.
Yeah, so I mean, there's a whole bunch of watt balances all over the world, and for that to actually replace the kilogram as a national standard, there's a couple things that has to happen.
Okay.
So first is they have to about half the measurement uncertainty around it. Half. Yes.
That's not a small amount. Yeah.
Sorry. Let's see how we're down. So right now, the watt balance is as accurate as 35 parts per billion.
Okay.
And before BIPM, which is the international sort of metrology group, accepts it as a primary standard, and has to hit 20 parts per billion.
Interesting.
And then they also had to correspond with, so there's another group that's working on it. So first you have to have all of these watt balances that are being deployed all over the world correlate. And the second thing is there's other people doing research based on counting atoms. Sure. And so that they want to be able to correlate to that too.
It seems like, go ahead.
No, I was going to say, that's the one I remember here. I've never heard about this watt balance thing. I remember hearing them saying that they're going to define it by X billion number of atoms of carbon or what have you, but then that's also, it's relative to the existing standard, and also how do you count billions of atoms accurately?
Right. Very carefully.
One at a time with
tiny
really
tweezers.
Yeah, there we go.
Well,
there we go.
the technology is there to do stuff atoms at a time. Like
It is, yeah.
I was talking to
nanorobots, yeah.
Guy who is what was he sold manufacturing equipment to chip manufacturers, and they were trying to lay the chips down one atom at a time to reduce error. So the technology is there for us to count atoms, right? It's not far away.
Do you think we can a throwback to a previous episode of this podcast? You should go watch it. When should we have an AI or some sort of computer system who is maybe monitoring this for us, because it might be inherently more accurate than we are?
Yeah, it seems to me like there would be some sort of like nanorobot type thing or some chemical reaction that has a very precise and known outcome that we could use to kind of batch process counting of
atoms.
Yeah.
Maybe, I don't know. It's beyond the scope of my job.
Yeah, because when you think of weight, you're talking commerce, and I actually never really thought about that angle. I've always thought about these standards in terms of science and measurements, but money is obviously a pretty big driver of our society. But what kind of accuracy are we dealing with today when we're talking about commerce of goods? I mean, it's not 35 parts per billion.
Zero.
Right?
0 parts per billion? Yeah. We don't know, right? I mean, we must have guesses based on statistical analysis of...
I'm sure the 2 gallons of milk you get at the store is maybe plus or minus a percent, right? And it's like, oh, we're okay with that.
Yeah.
So
how do we have an idea of how much the kilogram changes over time?
I don't have an idea, but I'm sure there are people in Gaithersburg who do, because we have our own... the United States has its own kilogram. It actually has
version.
2 kilograms that
deep in a vault of Maryland.
Yeah, in a vacuum somewhere there, and they will regularly compare them to the international kilogram as a transfer standard.
Okay, so because it seems to me like if they were all treated roughly the same, as far as we can tell, that there would be. I'd much rather have a dozen kilograms that we take a statistical analysis of over time, instead of just one that's like by law the kilogram.
And really, this is one of the big, I think, drivers of the watt balance. The other one is actually measuring very large and measuring very small weights. So if you think about it, we have a kilogram. So how do you get 200 grams? How do you get 200 milligrams? How would you measure that accurately?
Sure. Yeah, that makes sense.
And it ends up being like one of those riddles that you solved when you were in middle school.
Sure. Yeah. You have 1 cup and 5 whatever, and so yeah, it still kind of blows my mind every time I think about it that we're basing a standard off of a physical object.
Yeah, but to be honest, it's relatively new to do something different. So that it's only in the last 40, 50 years.
Interesting. I guess that makes sense. And I imagine this really matters a lot when, for a cup of coffee, like I don't care if it's plus or minus an ounce, right? It doesn't really bother me, but there are a lot of, chemical and radioactive type compounds out there that are very, very expensive in tiny, tiny amounts, and you may actually see some fluctuation in commerce of highly controlled, highly expensive.
Yeah, I don't. We can measure mass pretty well today, so I don't know that there's much that's currently being used commercial that is not that can't be measured sort of at least pretty well.
Okay.
But where we see is in like new research in pharmaceuticals and experimental physics and stuff like that, they need this, and this is all about sort of funding innovation in in the greater United States as well as enabling commerce. And what we see about science is once the technology is there, we start to use it, and
that makes sense.
It varies from field to field. So sometimes it's 20 to 30 years away. Sometimes it's electronics. Sure. A lot of it's like immediate.
Yeah. Okay, and we are actually out of time for today. So that brings us to our predictions section. So Matthew, do you have any predictions about the SI unit, or in general? I mean, what's the weather going to do?
Yeah, I think it's going to keep snowing here.
Yeah, it's so cold.
It was really pretty this morning on the way into work, actually. I liked it. It's like a little winter snow globe outside.
Yeah, it's going to be, I think it's a pretty good skiing year, too.
Yeah, for sure. Although those of us with young children are not getting as much skiing in as we maybe had hoped.
Yeah. Such as life.
Yeah, it's worth it. Okay, prediction?
I don't know. I don't know that I have a prediction.
It's going to keep snowing. All right. Hoffman?
I predict that this weekend I'm going to Breckenridge and I will have multiple kilograms of beer.
Sounds like a plan. My prediction is more related to measurement in general in the home, is that more and more people are going to start cooking based on weight instead of volume. So that's something that I've started doing when I like baking bread or something.
You're big on that.
I have a kitchen scale, and a scoop of flour or a cup of flour can weigh, vastly different amounts. So cooking on weight is my prediction. It's going to be more of a thing.
I was going to say I had a kitchen scale once, and then I put too much stuff on it, and it broke. So
I've seen your lunches, so
yeah.
I believe it. So those of you who don't know, maybe a little bonus content. Matthew used to be a semi-pro rugby player, and is working at Keysight and trying to bulk up 8 monstrous amounts of food.
Yeah, I had to consume something like 5,000 to 6,000 calories a day.
Yeah, it was a sight to behold.
Define a calorie for us real quick.
Yeah. That's a heat thing, right?
Yeah, it's a unit of measure.
Yeah.
Everything is derived off those 7 base SI units.
That's right.
Yeah. So now you know. Is there anything that you want people to do after watching this episode other than subscribing to the Keysight Oscilloscopes YouTube channel and the EEs Talk Tech podcast in your favorite podcast engine?
Yeah, no, I think that's just it. Subscribe.
All right. So we will see you next time. I think we're going to see Matthew again on EEs Talk Tech. So tune back in, and we'll see you later. Thanks for watching. All right. Can we do something with your water bottle?
Yeah. I mean, I can do this.
Hide it somewhere.
Yeah, that's pretty cool. I took the label off.
Yeah. Okay.
So